So we'll go to the next module where we wanted to look at two more architectures for image classification. These are GoogLeNet and ResNet. So here's a question, right? So consider the output at a certain layer of a convolutional neural network. So you have this layer after layer of convolutions and max pooling and so on, and you're at somewhere in the middle, and this is what your volume looks like. This is what your output volume looks like. Now after that, you could apply a max pooling layer, you could apply a 1x1 convolution, you could apply a 3x3 convolution, or you could apply a 5x5 convolution, right? And so far we saw that all these architectures, they do one of these things. They either do a max pooling, or they do a 3x3 convolution, or they do a 5x5 convolution, or a 7x7, 11x11, right? Any convolution. But they're all uniform. They're all either 3x3, or either 5x5, or either 7x7, right? So why choose between these options? Why not do all of this at every layer? Do you get the question that I'm trying to ask? Right? So far what we are doing is that you have this volume at a certain layer of the convolutional neural network, and after that you are either using all 3x3 filters, so you are using 256 3x3 filters or 512 3x3 filters, or using 7x7 or using 5x5. You are never using a mix of all these. So why not use a mix of all these? Why take a decision on that I only want 3x3? Because it's possible that you want to capture interactions at different levels, so you should have varied size filters at every layer. So how many of you get the question and the intuition that I'm trying to ask? Okay, good. So the idea here in GoogLeNet or in the Inception net is that why not apply all of them at the same time and then concatenate the feature maps, right? So I'll also do max pooling, I'll also do 3x3 feature maps, I'll also create 5x5, 11x11, and then just concatenate all of these together. So let's see how to do that, right? Now one problem with this naive idea is that it could result in a large number of computations. So let's see what I mean by that. So suppose the padding is 0, the stride is 1, then if you have a W cross H cross D input as the volume, and if you have an F cross D filter, then the output would be of this size. We all agree with this? This is the formula that we have been looking at. So this is the size of the output volume. Now every entry in this output volume requires how many computations? To get a single entry in this output volume, how many computations do I have to do? F cross D. So how do I get a single value? I apply a convolution at that value, and then I do those many computations. And here the number of computations is that I am going over this block of F cross D, doing a weighted multiplication and then adding them up, right? So you need that many computations. Everyone is clear with this? Okay, fine. So each element of the output requires these many computations, and we have so many elements in the output. Right? So you are doing really those many number of computations. Right? So can we do something to reduce the number of computations? Right? So that's the key idea that we need to focus on. So all of us buy the idea that doing this multi-granular or multi-sized filters is a good idea because you are capturing interactions at different layer. But I showed you that this is a problem with this. You can't just apply multiple filters. So let's see what we do. So what we do is 1x1 convolutions. What does a 1x1 convolution do? What does it make sense? How does a 1x1 convolution make sense? You have a pixel, I fit a 1x1 convolution on that, what will I get? I'll get back the pixel along the depth, right? So remember it's not 1x1, it's 1x1 cross depth, right? So what does a 1x1 convolution do? It actually aggregates along the depth. So this is what my 1x1 convolution looks like. It's 1x1 cross D. So I'll just fit that block on that pixel and do everything along the depth and get a single value, right? So from a 3D output, using a 1x1 convolution, I can go to a 2D feature map. Everyone gets this? Okay. Now I could use several of these 1x1 operations, 1x1 convolutions. In fact, I could use D1 of these such that D1 is less than D. So what effectively happens? The depth of the output reduces. So I take a certain output volume whose original depth was D. Now I take D1 1x1 convolutions, right? So I get an output whose depth is smaller than the depth of the original output, Is that fine? Everyone gets this? Okay. And you see how this will save computations, right? Because remember that this was F cross D, and now I have reduced D to D1. Okay, so it's going to reduce the number of computations. So that's what the idea is. You reduce it from F cross D to F cross D1, right? So that's this particular network, or this paper introduced the idea of this 1 cross 1. Actually, it didn't introduce it, used it, but it made it popular probably. Now, once you have done this, so this is how I'm going to proceed now. I have a certain volume. I have applied 1 cross 1 convolutions to it. Using that, I have reduced the number of dimensions. Now I'm going to apply 3 cross 3 convolutions as well as apply 5 cross 5 convolutions on top of that, right? Because that's the motivation that I had started with, that I want to apply kernels of multiple granularity. Now, can you think of some refinement to this? You see this branching over here. Why use the same 1 cross 1 convolutions before feeding to 3 cross 3 as well as 5 cross 5? I could use a different set of 1 cross 1 convolutions and feed it to a 5 cross 5. And use a different set of 1 cross 1 convolutions and feed it to 3 cross 3. Is that fine? What is the problem with this? Again, increasing the number of computations, right? But they found out that the trade-off between this is fine. Even if you're doing more 1 cross 1 operations, it still is okay. The number of computations are still manageable, okay? And then you could also do a max pooling, because we were choosing between these things, right? 5 cross 5, 3 cross 3, 7 cross 7, and max pooling. So we'll do all of these in parallel, and we'll also do some 1 cross 1 convolutions. So how many different types of operations we have done? We have done 1 cross 1, 3 cross 3, 5 cross 5, and max pooling followed by 1 cross 1 convolutions. Now all of these outputs that we have got a bunch of feature maps now. This is one set of feature maps, this is another feature maps, this is another, and this is another. All of these 4 we are going to concat together to get a single output volume. Do you see what is happening, right? It's all very mechanical. There's nothing really profound about what is being done. The only 2 profound ideas are, one is apply multiple kernels of different sizes, and the other is to use 1 cross 1 convolutions to make the whole computation manageable. These are the only 2 main ideas. The rest of it is not very different from what we have been doing. How many of you get this operation completely? Okay. So this block is called the Inception module. Okay, this entire thing is called an Inception module. So in subsequent slides, when I put an Inception module, then you know that these parallel operations are happening, right? So far, whenever we had seen a convolutional neural network, it was all serial, right? So you started with one operation, then another operation, and so on. Now you have an output or an input volume. You apply multiple operations in parallel and get one single output, right? So it's a parallel serial combination. Yeah. Okay. So we'll now see the full GoogLeNet architecture. So his question was basically 3 cross 3 would result in a different sized feature map, right? Because of, and 5 cross 5 would result in a different sized feature map. So he'll use appropriate padding so that all of this becomes equal. Okay. Okay. So this is how GoogLeNet looks like. So you have the input, again RGB, and same 227 cross 227 or 229 cross 229. Then you apply a convolution layer followed by a max pooling layer. Convolution, max pooling. Then you have this Inception module with a very specific configuration. So they have 96 1 cross 1 convolutions before feeding to 128 3 cross 3 convolutions, 16 1 cross 1 convolutions before feeding to 32 5 cross 5 convolutions, and so on. And I don't really see much point in going into the details of these numbers. There's hardly any intuition behind them. I again guess that it's, you try a bunch of things and this is the one which probably gave the best output. So the key idea is that of course you have this Inception module, which is a parallel module which does a lot of operations in parallel. This is again followed by another Inception module which has a different configuration, followed by max pooling, then again a few Inception modules, in fact 5 of them, again max pooling, then Inception, and this is the other interesting idea that they came up with. So at this point, remember in VGGNet, at the final layer, you had an output of size 5 and 2 cross 7 cross 7, right? And we said that this was a problem. How many of you remember this? Why was this a problem? Because I need to connect this to a fully connected layer, right? And that fully connected layer was of size 4096, right? So what they said is that what you could do is, instead of taking 5 and 2 cross 7 cross 7, for each of these 5 and 2 feature maps that you have, take this 7 cross 7 and just do an average pooling from there. What do I mean by that? Take these 7 cross 7 values, take an average of that. So now instead of 512 cross 7 cross 7, how many values will you end up with? Just 512. And in their case, instead of 1024 cross 7, you will just end up with 1024 values, right? So instead of looking at these dense connections with every pixel in the output volume, you just take the average of those pixels and then do a dense connection from there. So from this volume, you just go to a vector of size 1024, which is exactly this vector shown here. And from there on, life becomes easier, right? Because you have done a 50 times reduction in the volume. This was 1024 cross 49. Now you just have 1024 cross 1. So you have a 49 times reduction in the size. And that's a huge parameter reduction. And that actually worked very well in practice. They of course add these dropouts and other things. And then you have your fully connected layers. And finally the softmax layer at the output to predict one of the 1000 classes. Right? So this is the full structure of GoogLeNet or InceptionNet with multiple Inception modules. Right? So just remember that key takeaways are 3. One is have filters at multiple granularity applied in parallel. The other is use 1 cross 1 convolutions to reduce the number of computations. And the final one is to use this average pooling to make sure that you don't have this blow up of parameters at the output. Okay, so these are the 3 main ideas that you need to do, right? Okay, so this is exactly what I explained. So instead of having this nasty looking connection, which would have been 5016 cross 1000, you just take the average from this grid and just get a 1024 dimensional vector, which results in a much smaller weight matrix at the output. Everyone gets this? Okay? Yeah. So this is fine. So this has 12 times less parameters than ResNet. It has 2 times more computations, right? So that's what I meant by the trade-off. So the number of parameters has reduced significantly. Of course, a large amount of this savings happened in the fully connected layer. It's not the ingenuity in the Inception module which led to the fewer number of parameters. That actually leads to more number of parameters, right? But the reason they could afford more number of parameters in the convolution layers is because they reduced a lot of parameters in the fully connected layer. Do you get that? So they did this trade-off. And it has 2 times more computations than ResNet, but it's still acceptable because you see that there are many, many layers as compared to ResNet, right? So let's actually count the number of layers that we had here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So it has 14 layers, and each of these Inception modules is again like a split layer, right? It has these parallel components there. So having 2 times more computations was still an acceptable trade-off. And it of course led to much better accuracy as compared to ResNet or ZFnet or VGGNet, right? That we had seen in the original trend graph. Okay. So now we'll go on to the last architecture that we'll discuss for image classification, which is ResNet. So here's the idea behind ResNet, or here's the motivation, right? Now suppose we have been able to train a shallow neural network well. Now again, my definitions of shallow are relative. This is by no means shallow. There are many layers here, right? So you have some 8 layers here. Now if I have been able to do this properly, that means, what I mean by that is that using this network, at least I was able to reduce the training error to 0 or close to 0, some acceptable value. And I was able to get some reasonable generalization performance. That means on the test set, I was able to get some reasonable accuracy. That's what I mean by I was able to make this network work well. Now suppose I add a few layers to this network, and I have carefully added some layers in between here and in between here or over there, right? Now intuitively I could argue that if the shallow network was working well, right, then for the deep network there exists at least one solution which can directly come from the shallow network. Can you tell me what that solution is? I want all of you to kind of digest that idea. What the deep network could have done is, I know that this shallow network works. Why not I just behave like that, and I learn these parameters in such a way that I just end up copying from here to here. How many of you get this? Right? So there is a case for the deep network to do at least as well as the shallow network, and it could do the same thing at this point. All of you get this idea, right? So in other words, the solution space of the deep network, or rather the solution space of the shallow network, is actually a subset of the solution space of the deep network. There was one solution for the shallow network which could have been used as it is for the deep network. Of course, for the deep network, there are several other solutions because instead of the identity here, you could learn different things there. But at least that one solution exists. So I should, at least if I use this in practice, I should expect that this would work as well as the shallow network, right? Is that argument fine with everyone? Yeah. Oh, which has only one, yeah, of course, yeah. I mean, so those arbitrary things won't work, but here what they are, at least for the explanation intuition, right, you're using some reasonable things, right, you're just trying to make it compatible with whatever you have so far. So the argument is valid, right, so I can't expect that I had a volume whose depth was 128, and then I suddenly decide to use only one filter in the next layer, right. That means I have compressed everything, and now I expect it to be able to recur from there. That's not going to happen, right, so that's a fair argument. But the argument which I was trying to make, or at least for the illustration purpose, is that if you do reasonable things, and that's what people were trying out, right? This is the exact network that someone was trying out, and this did not work well. And I'll tell you what it is. So do you get his doubt and my clarification on that? Is that fine? Okay. So this is what was happening in practice, right? So you have a 20-layer network, a 32-layer network, a 44-layer network, and a 56-layer network. And you see that the training error of deeper networks is much higher than the training error of the shallow networks. That means this argument which I was trying to make, that the deep network should at least do as well as the shallow network, was not working well in practice, right? And if you think about it, it's not very surprising, because this argument hinged on the fact that it should be able to learn this identity mapping. But this identity mapping is one of many solutions, right? So for it to be able to narrow down on that solution, it's easy for you and me to think about it, but for the network, it does not have this intuition, right, that I can just copy it from there to here. Do you get that? The solution space is really large, and it's like finding that needle in a haystack, right? You have these many solutions possible, and I'm trying you to arrive at a solution where you end up with the identity solution. Is that clear? And it's not so easy for the network to do that. Everyone gets this? How many of you get this idea? Okay. So why not explicitly try to do something of this sort, where the network can actually learn some kind of an identity function. So now consider any two layers, by stack layers I mean this is a convolution layer and followed by a convolution layer, right? So these are two convolution layers back to back. So what do I actually end up doing here? I had a certain input x, and I'm learning some transformation of x through these convolution layers, right? So I'm trying to learn x, and then I was given x, I'm passing it through convolution layers, so I'll learn some transformation of x. And my argument was that if it could learn to directly copy x here, the deep network should at least work as well as the shallow network. So why not I explicitly ensure this? So why not I do this? That in addition to these connections, I also explicitly connect x to the output. Do you get this? So now what I'm trying to do this is hx is equal to f of x, which is the transformation that I learned for x, and in addition I also add x. So what am I doing? I'm explicitly feeding it the identity function, right? How many of you get the intuition for this? So what I'm trying to do is, I have a sense that if I could have transferred this x as it is across layers, then there's a chance that I should be able to do as well as the shallow network, right? So now I'm going to explicitly ensure that you learn these transformations, but I'll also feed you x at every stage at a reasonable time, right? So these are known as skip connections. So after every 2 layers, I'll feed back the x, or you could try after every 3 layers, I'll feed back the x. So I'm trying to maintain the original copy of x after every interval, okay? Fine. So why would this help? So this follows back from our argument, and that's the same thing which I said before. So using this idea of using these skip connections, these authors were able to train a really deep network of 152 layers, right? And this gave on multiple vision challenges, right? One being ImageNet, it gave 16% better results than the best network, and this is the one which reads that near human performance. Then ImageNet localization is another challenge where you need to localize the object. So there they gave 27% better than the best results. And there's these bunch of other vision tasks, detection, segmentation, and all of them. And in all of them, they significantly outperformed the best system using a very deep network. Of course, the downside is that you have a very deep network. It will take its own time to train and so on. But of course, if you are a Microsoft or a Google, you can afford to do that. So that's the current theme, right? I mean, the one with the largest computational resources wins everything, right? So, and they also had some other bag of tricks, which is not, I mean, it's not very difficult to understand. So they used batch normalization after every convolution layer. Have you heard of batch normalization ever in your life? Okay, good. They used Xavier by 2 initialization. Ever heard of that? Xavier by 2 was the same as He initialization, right? Then they use SGD, not any of the fancy Adam or Adagrad or anything, with a momentum of 0.9. Learning rate was set to 0.1 and divided by 10 whenever the validation error plateaus. The mini batch size was 256. They use a weight decay of 1 HT. What is weight decay? Weight decay is in the context of which regularization? L2. And what does this mean? Weight decay of 1 e raised to minus 5? The lambda was set to 1 e raised to minus 5. All of you remember these things, right? We did it in some previous course in some previous life. Okay. And no dropout was used, right? So since I have this here, I'll just say something more on this. So when you're reading papers on deep learning, right, focus on the experimental section where all these hyperparameters are described. So these are known as the hyperparameters. These are not related to the parameters of the model. These are related to hyperparameters, which is what the batch size is, whether you used L2 regularization, what was the learning rate, what was the optimization, and so on. So it turns out in many cases, if you don't stick to this, you will not be able to reproduce the results of the paper, right? So you might be wondering that, okay, this network I understand. This is just 152 layers and I can just keep adding skip connections. I can easily code this up. But I'm not getting the same results as the original authors of the paper. So this is where you need to dig up then, right? You need to look at the experimental section where most good authors provide these details of how they have trained the network, how many epochs did they use, what was the patience set and all that. If you follow those, the chances of reproducing are much, much higher. Still not guaranteed, but definitely much higher, okay? Okay, so that's where we end the lecture on convolutional neural networks and ImageNet classification.